Motor protection circuit breakers, or MCPs, can be used with motor loads if specific conditions are met. The most important condition is that there must be overload protection at the motor end of the feeder circuit. This protection is typically provided by a motor protection relay or an overload device that is integrated into the motor controller. Secondly, the feeder circuit itself must be sized appropriately. Specifically, the feeder circuit must be rated for at least 175% of the motor's full load amps, or FLA. This ensures adequate short-circuit protection. Thirdly, a cable supplying the motor must be rated for at least 125% of the motor's FLA. This prevents overheating of the cable. Regarding the cost difference between MCP and thermal magnetic circuit breakers, the difference can vary depending on several factors. These include the size of the breaker, its rating, and the manufacturer. Generally, MCP tend to be more cost-effective than thermal magnetic breakers for larger sizes, typically those above 600 amps. However, for smaller sizes, the cost difference may be minimal and possibly negligible. In a situation where overload protection is already provided at the motor end, and the feeder circuit and cable are sized appropriately, using MCP becomes a viable option. However, it's crucial to carefully consider the cost difference between MCP and thermomagnetic breakers, especially for smaller sizes. If the cost advantage is not significant, thermomagnetic breakers might be a more suitable choice due to their simplicity and ease of installation. When dealing with electrical systems and motor loads, it's essential to adhere to relevant electrical codes and standards, such as those provided by the National Electrical Code. These codes provide guidance on proper sizing, protection, and installation methods. When selecting between MCP and thermomagnetic breakers, it's important to consider the specific application, the motor's characteristics, and the overall system requirements. Factors such as starting current, operating conditions, and potential fault current should be taken into account. Furthermore, it's recommended to consult with qualified electrical engineers or professionals who have expertise in motor control and protection. They can provide valuable insights and recommendations based on their knowledge and experience. In summary, MCP can be used for motor loads if overload protection is provided at the motor. The feeder circuit is sized at 175% of the motor's full load amps, and the cable is rated at 125% of the motor's full load amps. The cost difference between MCP and thermomagnetic breakers should be carefully evaluated, and the choice should be based on a comprehensive assessment of the application requirements and electrical codes. Remember to consult with qualified professionals for guidance and ensure safe and reliable operation of the electrical system. When considering the use of motor protection circuit breakers, or MCPs, it's crucial to understand their specific purpose and how they differ from thermomagnetic circuit breakers. MCP are primarily designed to provide short-circuit protection for motor circuits. They are not intended to provide overload protection. Overload protection is the responsibility of a separate overload relay or device that is installed at the motor end of the circuit. Thermomagnetic circuit breakers, on the other hand, provide both short circuit and overload protection. They use a thermal element to detect overloads and a magnetic element to detect short circuits. This dual functionality makes them a versatile choice for general-purpose circuits. However, in motor circuits, where overload protection is already provided by a separate device, MCP can be a cost-effective option for short-circuit protection. When sizing MCP for motor circuits, it's important to select a breaker that is appropriate for the motor's full load amps and starting current. The breaker should be able to withstand the motor's inrush current without tripping, while still providing adequate short-circuit protection. Typically, MCP are sized at 175% to 250% of the motor's full load amps, depending on the motor's design and starting characteristics. It's also important to consider the interrupting rating of the MCP. The interrupting rating is the maximum fault current that the breaker can safely interrupt. The interrupting rating should be high enough to handle the available fault current at the breaker's location. In many industrial and commercial applications, high fault currents are common, so it's important to select MCP with adequate interrupting ratings. When installing MCP, it's crucial to follow all applicable electrical codes and standards. This includes proper wiring practices, grounding, and enclosure requirements. MCP should be installed in a suitable enclosure that provides protection from the environment and prevents accidental contact with live parts. Additionally, it's important to label the MCP clearly to indicate their purpose and the circuits they protect. This helps to ensure that the electrical system is safe and easy to maintain. When comparing the cost of MCP and thermal magnetic circuit breakers, it's important to consider the overall cost of the system. While MCP may be less expensive than thermal magnetic breakers, the cost of the overload relay or device must also be factored in. In some cases, the total cost of the MCP and overload relay may be higher than the cost of a thermal magnetic breaker. However, in other cases, the MCP approach may be more cost-effective, especially in large systems with many motor circuits. It's also important to consider the long-term maintenance costs of the system. Thermal magnetic breakers are generally more reliable and require less maintenance than MCP and overload relays. This can translate into lower operating costs over the life of the system. Ultimately, the decision of whether to use MCP or thermal magnetic breakers depends on the specific application, the motor's characteristics, the system requirements, and the cost considerations. It's important to carefully evaluate all of these factors before making a decision. It's also recommended to consult with qualified electrical engineers or professionals who have expertise in motor control and protection. They can provide valuable insights and recommendations based on their knowledge and experience. In summary, MCP can be a cost-effective option for short-circuit protection in motor circuits, provided that overload protection is provided by a separate device. When selecting and installing MCP, it's important to consider the motor's full load amps, starting current, interrupting rating, and applicable electrical codes and standards. It's also important to compare the overall cost of the MCP approach with the cost of using thermal magnetic breakers. Remember to consult with qualified professionals for guidance and ensure safe and reliable operation of the electrical system. Furthermore, when discussing the application of motor protection circuit breakers, it is good to understand the coordination and selective tripping aspects. Coordination refers to the ability of the electrical protection system to isolate a fault to the smallest possible area, minimizing disruption to the rest of the system. Selective tripping means that only the circuit breaker closest to the fault should trip, while upstream breakers remain closed, maintaining power to other circuits. When using MCP with separate overload relays, coordination can be achieved by carefully selecting the time current characteristics of the breakers and relays. The overload relays should be set to trip before the MCP, ensuring that overloads are cleared before a short circuit occurs. The MCP should be selected with a short time delay to allow the overload relays to trip first. This prevents nuisance tripping of the MCP during temporary overloads. Coordination studies are often performed to verify that the protection system is properly coordinated. These studies involve analyzing the time current curves of the breakers and relays to ensure that they will trip in the correct sequence. Coordination studies can be complex and require specialized software and expertise. When using thermal magnetic circuit breakers, coordination is typically simpler to achieve, as the breakers provide both overload and short circuit protection. However, it's still important to select breakers with appropriate time current characteristics to ensure proper coordination. Another important consideration is the ambient temperature in which the breakers and relays are installed. The performance of these devices can be affected by temperature, so it's important to select devices that are rated for the expected ambient temperature. Temperature dating factors may need to be applied to the breaker and relay ratings to account for high ambient temperatures. It's also important to consider the altitude at which the breakers and relays are installed. Altitude can affect the dielectric strength of the air, which can impact the interrupting rating of the breakers. Dating factors may need to be applied to the interrupting rating to account for high altitudes. In addition to the electrical characteristics of the breakers and relays, it's also important to consider their mechanical construction and environmental protection. Breakers and relays should be selected with enclosures that are appropriate for the environment in which they will be installed. For example, in wet or corrosive environments, breakers and relays with NEMA 4 or FOX enclosures should be used. The enclosures should provide protection from moisture, dust, and corrosive substances. It's also important to consider the ease of maintenance and testing of the breakers and relays. Breakers and relays should be selected with features that allow for easy testing and maintenance. For example, breakers should have test points that allow for easy measurement of current and voltage. Relays should have self-testing capabilities that can detect potential problems. Regular testing and maintenance of the breakers and relays is essential to ensure their reliable operation. Testing should be performed in accordance with the manufacturer's recommendations and applicable standards. Maintenance should include cleaning, lubricating, and tightening of connections. In summary, coordination and selective tripping are important considerations when designing and installing electrical protection systems. When using MCP with separate overload relays, coordination can be achieved by carefully selecting the time current characteristics of the breakers and relays. Thermal-magnetic circuit breakers typically simplify coordination. The ambient temperature, altitude, mechanical construction, environmental protection, and ease of maintenance and testing should also be considered when selecting breakers and relays. Remember to consult with qualified professionals for guidance and ensure safe and reliable operation of the electrical system.